So yeah, today I'm going to talk about AvaFrame, the Open Avalanche framework, which is a cooperation between the Austrian Research Center and the Austrian Avalanche and Torrent Service, basically the VLV for those who know that. So basically the VLV pays, this is the operational side, and VFW actually puts the project into motion. So to start a little bit, I have to start with a little bit of history, and I know history is not everybody's favorite, but well, it's important for the project itself. A bit of information about the Austrian Torrent and Avalanche Control to give you a bit of a background why it started. So the main mandate here is natural hazard protections for settlements, basically, and this means we're talking about stuff like hazard maps, we're talking about building permissions, and so on and so forth. So this is the background of what's needed. The VLV itself is concerned with all gravitational processes, but here we are only focusing on avalanches. And contrary to what's being used in Norway, we are talking about 150-year return level. So these are the extreme events that we are talking about, and avalanche sizes above 10,000 cubic meters. That's the characteristic that's behind it. And yeah, so we are talking about avalanches like this, where you see in purple an avalanche that came down. There's a settlement to the left. This is going to be painted in roughly the red and the yellow zones. So red means no building allowed, and yellow is where the buildings are, and you see a dam that's protected this settlement. This is what we are concerned about. This is the background of the VLV. Now let's talk about the avalanche modeling history. So in 1995, a development on a new avalanche model started in Austria, which was called then SamosAT. And then in 1999, Galtür happened, which is a big avalanche disaster with about 40 people, which left 40 people dead in Austria. And this kind of kickstarted even more development, and this kickstarted the whole hazard mapping in a well-organized manner. In 2004, for those who, some of you might be familiar with it, SamosAT was started and was released in 2007. So SamosAT, I will get into this a little bit more later on. And also RAMS is very familiar in our community. So this started in 2005, and in 2008 it was released the first time. And then in 2016, first discussion started for a new model. And in June 2020, we actually started working on AvaFrame. And as a background for Samos, this was started off as engine simulations. So the engine that is behind it, the numerical engine that is behind it, started actually from engine. So trying to optimize fuel consumption and so on and so forth. That's why you will sometimes see some references to this. So what does AvaFrame actually want to do? So our mission is, and I'm going to read this to you, to develop an open source framework, and again, for avalanche simulations. And this tries to replicate and simplifies current procedures at the Austrian Torrent and Avalanche Control. So, and these are two important things, which replicates and simplifies, and the current procedures are what's interesting at the moment. So what are the goals of this? The goal, first of all, is we want to make the model and the ideas and the knowledge available and make it possible to be able to be maintained. We also want to transfer new developments to operational versions. So not to lose anything that's done in development, and because there's a lot of interesting stuff out there. And this also then sets the spectrum of what we want to do. We want to do operational, scientific, and also educational use. And since it's being a framework, we are talking about multi-domain and multi-model. So we're not only looking for one special use case, we are trying to cover multiple domains, and we're also not only using one model, but we try to diversify it a little bit more. And yes, I know there are other models out there, and as always, as it is with standards, you try to get something together and make it build a new standard, and you just end up with more standards. We know that, and we are aware of that, but we somehow try to still add to the discussion. So the question is, what do we do differently than all those other models? So the first one is that, or the biggest one, I think, and I'm going to answer that question at the end, that we're trying to be open source. That includes the data and the access to data as well, and application and so forth. And we kind of want to accept all the knowledge that's out there. But I'll get back to this later on. So first of all, what are we concerned with? We are concerned with the classical case of having an avalanche and a release area at the top. In the background, you see the topography. And then you release this avalanche, and it ends up down at the bottom somehow. I'm going to quickly switch over to video. So you see here a simulation of particles. On the left-hand side, you see the upper area of the topography. You see the particles and their mass, and on the right-hand side, you see the whole avalanche, and you see how the particles flow down the mountain. We tracked one of those particles to show where one particle end up, and this is basically one of the core functions that set the base for everything. And this is done as it's being done in SamosAT as well. I'll get to this now. So, but our framework is a lot more than this. We not only want to do these simulations of dense flow avalanches, we also want to include other stuff. We want to include statistical models. We also want to make open source test data and benchmarks. We want to open source tools for analysis. And also important, we want to have a good documentation on all of this. So one of the core components, for example, is testing, in which we provide test cases. So we think that it's very important that if you implement a new model or if you improve a model, that you properly test it against some reference simulations. And this is usually done behind closed doors, and then it's decided it's good, and then it's released. So first of all, we provide test cases that are idealized. So it's just a chute or a slide or a flat plane, or you can think of a lot of things that you can use for these. And we provide, first of all, we provide tools to generate these topographies, but we also provide test cases in which we utilize some of these. And we also provide real avalanches. So these are topographies from Austria, and there's 6 at the moment. We're currently extending this. And for these test cases, we provide the topography, we provide input data like release area, entrainment areas, and things like this. And then it's up to you if you want to, what type of the data you want to use there. Plus, we also provide the test infrastructure and tools to analyze this. And how can this look like? This is an example now. The figure itself is very overloaded, but these are figures that we produce and that we use in constant model development. And I just want to draw your attention to the upper right side. So here we have 2 simulations, and they are transformed so that you can actually compare them. And we have a reference and simulation itself. In here you see the dashed lines and the full lines, and these are the 2 simulations. And this allows you to quickly analyze: does your change of the code, does your change of the input, does it actually have some influence on the result? And these are figures that are being produced standard. One note on figures that we produce: we try to use a general set or produce a general set of images that you can use and combine, but the main idea is that we also provide the data. So if you want to analyze it in a different kind of way, then do so. We don't try to cover all the use cases, we try to cover our base use cases. Then let's get to one of the core components, which we call com1DFA. This is a module that is used for dense flow computation avalanches. And the basis of all this is SamosAT. It's particles, so it's a Lagrangian view of modeling. It's depth integrated, so there's a shallow water assumption behind it. And we use smooth particle hydrodynamics numerics. If you want to know more about this, we have a documentation out there. We're also trying to publish a paper soon where the theory and the mathematics behind it are fully explained. So I point you to this if you want to know more about this. And since quite a few of you might be familiar with SamosAT, there's the question now, what is the difference between SamosAT and AvaFrame? And as a background, SamosAT was developed, as I said, basically 20 plus years, and it's in full operational use since then. So there's a lot of knowledge about this available. SamosAT allows you to dense flow avalanches and powder snow avalanches. And we kind of spun off Samos Beta, I think 2 or 3 years ago, where you get a dense flow standard setup simulation. So you can use this without any license requirements. But it was not open source. It was just free for you to use. And this is being kept at the moment in AvaFrame. If you ever stumble upon it, it's COM1DFA Oryx. So this is a standalone dense flow kernel from SamosAT, which is C code. You can actually use it. The executable is available, but we will get rid of it soon, and I'll explain why. Because we now switch to our own implementation of the dense flow, and we switched over to Python and Cython, so it's a little bit easier to read and a little bit easier to extend. And this one is fully open source. So if you look at our source code, you will find this completely there. And if you change something, this is as a background. So what we do, or what we do have, is this structure basically. So we have components that are within AvaFrame, like input stuff, preparation stuff. Then we have the computational modules, and we have some output modules. The way we want to control this is we say, and I'm going to do this later on as well, we have 2 ways of controlling at the moment. Either you can use QGIS as kind of like an interface, or you script it yourself. So we are not trying to build a good interface for it. We're trying to build the base, which you then can use to build your own interfaces if you want to. And the idea behind this, now you have all these modules and information, which is fine for scientific and testing research, but we also want to have an operational arm, so to say. So we want to use all our developments also in application in daily use. And this means that we pick a certain path within the framework, and this is what we then call our operational setup. This is then the tested one for public use. And here's an example for the operational use case. This would be an example picture out of QGIS, which you use in your reports. So we provide base information about the peak pressure, peak flow velocity, and the peak flow thickness. And then you would also use some other models and combine this information, and then you do your recommendation for hazard mapping, whatever you need for. And here's a note. So this is tested, of course, for Austria, since the money comes from Austria. We're not specifically targeting Austria. We think that it's applicable in other areas as well. But if you want to use it, then please make sure it's also applicable to your areas. But, and this is important, the parameters are fully adjustable, so you can actually play around with if you want to. What we also try to push out to operational use is we want to work more towards, instead of using these like here with the peak flow pressure, you have this one result and that's it. We want to push more towards a bit of the sensitivity and probability, and we also provide these tools in AvaFrame. So saying that if you vary, for example, release thickness, how does that influence the runout itself? And then you can make statements like, for example, here on this side, you don't have any influence. On the front, you have some more, and we show how much influence it actually has. So in this plot, blue means that basically all our avalanches hit this spot or this pixel, and then the lighter it gets, the less avalanches are being in this pixel. And this is something we think should be used more often to actually show the uncertainty of the model, and it should also show the uncertainty or the sensitivity of the input data that is being used for hazard mapping. And now I'll show some examples from the research side. So one of them is using a radar, georadar, and this is up above Innsbruck, and it's a field measurement project quite some time now. And you get some information. So on the lower right side, you get the MTI plot for a radar, for example. So this gives you an information of time versus distance where the avalanche is and how much information there is in this avalanche. And we are trying to do synthetic radar-grams. So basically trying to see whether our model can produce a similar MTI plot, basically. On the upper right-hand side, you see the outline, what comes from the MTI plot of the radar. And below that, you see the flow velocity of our avalanche. And we started working on this. And since a temporal evolution is always interesting, we are now trying to introduce a target time diagram, which basically, instead of just showing this one snapshot of peak flow velocity or whatever you use, or use animations to actually flip through a simulation, we want to offer this up in one plot. So you can see this is time on the x-axis versus distance to the beta point. So this is a 10-degree point in this case to have a reference point. And we then display the average flow depth or flow thickness of this simulation. And you can see in black, this is the avalanche front. And then you see different information. So you can see that, for example, at minus 1,000 meters, the avalanche hit at about 20 seconds. And then the most of it was flows through it. And then about at 20 seconds, 10 seconds later, most of it is through. And then it's just only like these little slides behind. And these are the informations that we try to convey. So you see a temporal evolution of what the simulation actually does. And again, this is not observation. This is simulation. And you also get information about approach velocity. Then another example, still very applied scientific, is Avalanche. So Avalanche is also done up on the Notkette, in which these Ava nodes are being dropped into the release area. Then avalanches are artificially triggered, and these nodes are being tracked via radar and via satellite. And then you try to analyze this and see what's happening. So here's another video about this. So this is the Notkette itself. You see the release area here. It's being triggered. And then you see it flowing down, and you see three bigger particles, and these try to represent the Ava nodes, so that we then can try to compare the velocity of these nodes versus what the velocities does the simulation deliver. And there's also a radar that does try to track the avalanche itself. And this is still an ongoing project, but it kind of shows the application side of things. If you want to know more, I recommend you try to search for Neuhauser at the EGU 22, where he had a talk about this avalanche, and it's still an ongoing project. Then let's dig deeper into a little bit of modeling development, where we try to still be applied to applied developments. And one thing that we started now is trying to automatically generate avalanche paths. Why are these important? I mean, most of you will be familiar with the alpha beta model, and it's also in use in Austria. But sometimes when we do simulations, we don't have a path as such, and users don't want to provide it. So what we try to generate is an automatic path. So on the left-hand side, on the lower left-hand side, you see the peak flow velocity of an avalanche. And with these dots, you see a mass-centered path that we generate. So what we do basically is we run a simulation with a certain base parameter set. And then from this result, we extract a path. Then we have to extend it to the top and the bottom, because of course, if you do mass averaged, you will end up somewhere in the middle. And these paths we then play back to the users so they can actually use it or say, no, that's crap, I don't want to use it. So this is what we try to do. We also try to discern automatic split point. Split point being the one from there on you start searching for the beta point, the 10-degree point, and we also try to automate this. And why are we trying to do this? Because we want to push our operational people to always try to use multi-model, to not only look at one single model, but doing it automatically with different models so you get different puzzle pieces which you then can combine. This is basically being done in Austria anyway, but it's done manually, and we want to introduce this that is being done more automatically. And then something that goes really, really deep into model development. This is also what we do. This is then trying to basically improve or extend on the or investigate in the model itself. Is that we also provide test cases with known solutions. Because I mean, you don't have any reference solution apart from events for real avalanches. But to verify numerics and to do numerical investigations, you also have to have, or it would be best to have analytical solutions, let's put it that way. And two of the ones we provide is a similarity solution and a dam break. So similarity solution left, where you just have an inclined plane and you have a pile of snow which you let flow, or a pile of matter if you want to. And on the right-hand side, you have a dam break. So you start with a kind of like a rectangular box shape at the beginning, and then you just let it go and you see how this then develops. And for these quasi analytical solution exists, and with these you can do comparison with your runs in your numerical. So basically what you do, you vary a parameter, you run these simulations, and then you can do analysis on the error, and you visualize this. And for us, this was example being used for checking whether our numerics converge. So this is basically, we're not looking at anything that's done in real life or in real life scenarios, but it's also important to know what our numerics do. And if we look on this plot here now, you see that we varied the number of particles on the x-axis, and on the y-axis we have the relative error. So this is basically the error management. And at first we start with a time step of 0.2, and we see the more particles, so the more information I add. If you look at grid models, this would be the resolution. And the more particles you add, the less error you should get. And you can see that we get this. The more particles we add, the less error we get. And this is all done on flow thickness for now. And then you increase the time step, which is also, if you come from Linux, you know that if you lower the time step, it should also converge. And you can see each of these time steps then in the next step actually improves on the result. So we can say, yeah, our model is convergent. So at least there's no numerical problem. So, and these are all these applications that you can have. And as I said, this is a bit of an overview. It's not extensive and it's not all that we did, but these are the areas that we can work with the AvaFrame, and this is what we try to invite other people to do as well. So if you want to actually try it, you have two ways of doing it. The one which we call the standard of operation one. This is what we call our well-calibrated setup for hazard mapping. So this is the thing that's being used at the WFV. You control it via QGIS, and this is being stable. And you're only allowed minimal parameter adjustments. So in this, you can provide release areas, you can provide release heights, you can provide entrainment areas, for example, but that's it. All the other parameters that are there are set to a fixed value, and this fixed set of data of values, this is what we call the operation setup, and we try to change this as little as possible, and we improve on it when we actually feel very confident that our results are better. So this is, if you want to do it, use it for hazard mapping or for applications, this is the way for you to do it. There's a QGIS plugin as well, and the installation is fairly straightforward for this. But then on the other hand, you might be interested in testing it or working with it a little bit more, experimenting with with it. And this is what we call our developer installation. This is where you want to work on the code itself. You want to implement your features. And this is the one that might be unstable. So if you try something that worked in this version, it might not work in the next version. This is something that can happen. So you have to be aware of that things might go wrong. And it's a little bit more involved for installing, but we still think that it's very easy to install. And for both, if you ever have any questions, just contact us and we might be able to help you. And then a word about the license, because I mean, this is important for people who want to apply it. So we published it under the European public license. And there are the permissions that you have. You can fully use it for commercial use. You can put modifications on it. You can also use it without ever telling us, so the private use is there. The conditions that you have, they always apply. You have to disclose the source. So if you publish anything, you have to say it comes from AvaFrame. You have to put up a license and copyright notice. And if you modify it and publish it, you have to use the same license and state the changes that you applied. And as always, the limitation that there is that there's no liability or warranty from the AvaFrame project. So basically, it's you can do what you want with it, but it's your own fault. That's what we always say. The resources you can use, first of all, our documentation. Find the links on here. You can get the code and you can submit issues if you stumble upon anything or any problem as well. And we do announcements and the communication a lot via our homepage, avaframe.org, where we also try to put up monthly updates of what we're doing. We're sorry, at the moment we're 2 months behind because we're rearranging the homepage a little bit, but there are some more announcements coming up soon. And if you want to contact us, I mean, you can use the normal channels of using email, or you can contact us via Matrix environment chat. So what are the conclusions to this? So the version 1.1 is out at the moment. It's in use operationally and scientific. And this is something that I want to mention earlier, is when I talked about SamosAT and our version, up to version 1.0, we always try to exactly hit what SamosAT does. And why are we doing this? Because we want to use this in operation. So we don't want to lose all that knowledge that was collected during 20 years of time. We actually want to be able to replicate this. And from now on, we are mainly developing only AvaFrame. And if we have improvements, we will add this, and now it will diverge from SamosAT. As I said, AvaFrame is open to your contributions. If you want to add new features, if you have ideas for new features, if you want a new help or tools, feel free to contact us. If you want to use it for investigation into certain topics, please do so. The outlook that we have at the moment is that in the near future, we want to include other external code, like, for example, some of you are familiar with FlowPy. We want to make a connection to AvaFlow to have this multi-model even more extended. We are currently working on papers, and we're trying to push this probability sensitivity analysis into our operational setting. So the question I started at the beginning is, what do we do differently? So I said, then we're going to use open source and we accept all the knowledge. But the thing that I think we want to try to do differently is we want to apply it operationally as well. So there are plenty of other open source models out there, but hardly any of them are used in operational settings. And we're trying to change this to always keep this, to get in new information and then also give it out that we're actually using it. And if you ask me personally what we want to reach in 5 years' time, any project should have this. It should take over the world in this time. And with this, I want to say thank you for your attention.